This video is about vector fields. Vector fields, just another type of functions. So before we talk about that, let's list all the functions we learned so far. The first one we learned is y equal to fx. X there is called independent variable and y is called dependent variable. And for this simple type of function, x is a scalar, one-dimensional. So is a dependent variable y. Okay. Example for that, y equal to x squared. Okay. So what's the graph of it? Give x, you find a y. Give another x, you find another y. You connect those points, you get a curve. Okay. Second type of function we learn is RT. I put the arrow on the top of R means R is a vector. So it's a vector could have like 2 components or 3. Let's say 3. Okay. Or you can write in this form: ft I is a vector, okay, plus g of t j plus h of t k. Okay, for this type of function, independent variable is t, which is a scalar, but dependent variable r is a vector. Okay. So what's the graph of that? We learned this in this class. Okay. So you can imagine, for giving this really is your x, y, and z. Okay. So for giving t, you plug in these 3 functions, f, g, and h. You will get a point, x, y, z. You got a point in the space. For different t, you got a different point. So if you connect all those points, you got a curve in the space. Okay. We call this is a parametric form of the curve. Okay. So in other words, this type of function, independent variable is scalar, but function itself is a vector. Okay. And which give you a curve. Okay. Then another type of function we learn is, say, z equal to fxy. Okay, this time for this function, independent variable have 2, x and y is a vector, but the function itself is a scalar. Okay. Dependent variable z is a scalar. Okay, so what's the graph of that? That's what we just learned. Okay. Given xy here on the xy plane, you plug in there, you find a z. For different x, y, you find a different z. So you think about this is your domain. Then you will have like a surface above that. Okay. So this function gives you, for this type of function, independent variable is vector, dependent variable is scalar. Then you got a surface. Okay, what we're going to learn today is something like this. I put the arrow on the top of f, means f itself is a vector. You can write, like, say, 2 component. Could be 3. Okay. In the book, they call it P and Q. Let me do that. P and Q. It's a P. Or you write Pxy I plus Qxy j. Okay. So we call this kind of function vector field. Okay. So this function is more complicated because independent variable is a 2-dimension, x and y, could be 3. And so is a dependent variable f. F have two components. One is a P, one is a P, one is a Q. Okay. So what's the graph of that? It's a graph with a vector field. For example, say f x y here equal to minus y I plus x j. In the other words, it's a minus y x. Okay. Its graph is a vector field x and y. For example, I pick a point. Say here's a 1 and 0. You plug in here. You will find your f 1 and 0, which means when you see x replaced by 1, when you see y replaced by 0. So the first component is 0, the second one is 1. This sense itself, 0, 1 is a vector. What this vector looks like? Okay, what is a vector? Endpoint is this is 0 and 1, so that's what that vector is. This vector. Okay, now remember, vector can be, doesn't matter what is starting points, so that's what we have. Then for example, at this point 0 and 1, what is f 0 and 1? They give you replace x by 0, replace y by 1, so you got a minus 1, which give you this one. So basically at every point for given x, y, you plug in there, you get a capital F, which is a vector. So its graph is a vector field. That's why we call this a vector field. Why we want to learn something like that? Because lots of the variables in the real world are vector field. For example, velocity. Velocity itself is a vector. Okay. So, like say, at a different point, your velocity will be different. So that's a vector field.